Alright, so in this video I'm going to talk about atoms and elements, and you're probably going to learn far more than you ever really wanted to know about them. Alright, so let's first talk about and look at atomic theory. What is atomic theory? Well, it's the theory of the atom. Go figure. It says that atoms are tiny particles of matter. They're made up of subatomic particles. In fact, there's 3 subatomic particles that we know about. Protons, which are positively charged, electrons, which are negatively charged, and neutrons, which, like their name, are neutral. As you might expect, like charges repel. So for instance, if I had 2 negative electrons sitting next to each other, they're going to repel each other. 2 positive protons, they would also repel each other. But if I had a positive and a negative, they're going to attract each other. So what does that mean? Well, my protons and my electrons, opposite charge, they're going to attract each other. But as we're going to see in a little bit, where they actually sit in different locations. Okay, let's talk here at the bottom of the slide, the size of an atom and the size of the nucleus. The nucleus is really tiny in comparison to the space, what we call the volume, that an atom takes up. Down here, I have this little analogy here. It says roughly a football to a football field in area. So what that means is, imagine you were on a football field, or at least looking visually, think about a football field and how big it is. And then you've got a single football sitting somewhere on the field. The single football is the nucleus. The field is the space that the entire atom takes up. So what that means, really, what does that come down to? The nucleus is really tiny in comparison to the space that an atom takes up. Well, what in the world's in the extra space? Well, that's what we're going to talk about here in just a little bit. All right, so these are my 3 subatomic particles, the proton, neutron, and electron. You can see their symbols and a couple of things that are really important, and it's these 2 columns right here. The charge, so electrons are negatively charged. That's why the symbol is the E with a negative sign. Protons are positively charged, hence their symbol, or one of the symbols that's used. And then neutrons, as we said, are neutral. That'll be important in just a little bit. Okay, the other thing, the mass, the approximate mass. What do we need to look at here? Well, here's what's important, and that is that the mass of the neutron and the mass of the proton are both the same. So they have the same mass. Now, check this out. Look at the mass of the electron in comparison to 0.0005, or 1/2000th of an AMU. So when we're talking about mass, okay, we use this arbitrary unit AMU sometimes, which just means as a comparison to, it's atomic mass units. But when we're doing our numbers, which we'll do here in just a second when we're looking at different elements, we're going to use the mass of 1 for proton, 1 for neutron, and we're going to go ahead and just say that the electron has a mass of 0. I promise it'll make our calculations a lot easier. Now, one thing I haven't talked about, and that is the location of the 3 subatomic particles in the atom. So the protons and neutrons, they sit inside the nucleus, and these electrons, as we're going to learn about, the electrons are moving around outside the nucleus. And if you go back to that analogy on the previous slide about the football field, what this means is that if the nucleus is my football and it's really tiny in comparison to the football field, the rest of the atom is made up of electrons, and in fact they occupy the vast majority of the space that an atom takes up. And again, we're going to learn more about the electrons and how they sit and where they go in just a little bit. The mass numbers over here, these are in grams. Okay, notice they're really tiny numbers. For our purposes, we're not going to use these numbers in this class, but if we were to measure things in grams, that gives you an idea. G again is gram, but that probably doesn't mean a whole lot to you. Let me give you a comparison. 1 drop of water weighs, I don't know, it weighs about, let's say, 1 tenth or 0.1 grams. 1 drop of water weighs 0.1 grams. Give or take, I'm just guessing on that one, but it's pretty close. Now look how small these numbers are. So if I had a drop of water, and let's say it had a mass of 0.1 grams, if I were to put that into scientific notation, it would be 1 times 10 to the minus 1 grams. This is 10 to the minus 24, 10 to the minus 28. Wow, a whole lot different, isn't that? A whole lot different. All right, let's talk about elements. Elements, those things on the periodic table, we're going to look at that in a minute. But the definition of an element: pure substances, they cannot be separated into simpler substances, those subatomic particles, for instance, that we were just talking about, by ordinary lab processes. They're building blocks of matter. And these are just some different examples. Gold, you know what a gold ring looks like, for instance. I'm sorry, these are off a little bit. Aluminum, those are like pieces of aluminum. And carbon, there's some carbon shavings. Now, what's interesting, especially about carbon comes in many forms, and a lot of elements come in many forms. Carbon, depending on the way the atoms are arranged, carbon can be in the form of graphite, you know, like pencil lead, or, ladies, you know what these big shiny things are? Diamonds. Graphite and diamonds are both made up of carbon and only carbon. But boy, aren't they different. I don't know about you, but I wouldn't be thrilled if some guy gave me a ring made up of graphite. Well, what's the difference between graphite and diamonds? Again, both made up of carbon, but it's the arrangement or the pattern or differences. That's all. All right, here's the periodic table of elements. It's kind of a snapshot. I pulled some of it out here. Here are just some common symbols and their names. Okay. You've got a periodic table with the names of the elements. I've put it in the class. Make sure you use it. You don't have to memorize the names. There's no reason. And always make sure you look up, especially when you start naming things, make sure you look up and grab the correct name for the correct symbol. So the question, do I need to know all of them? Nah, you honestly don't have to memorize anything. Let's talk about some other things in regards to the periodic table. The periodic table has these columns, also known as groups. Okay, fancy name is group, but technically they're columns on the periodic table. And you can see group 1A, 2A, 3A. There's columns down here too. But some of the groups, not all of them, some of them have nicknames. And let's talk about that here for a second. So, for instance, on the far right-hand side of the periodic table, the far, far right, this column here where helium and neon are at the top of, those are the noble gases. These are nicknamed, I like to say, noble gases. Sitting next to them, where fluorine is at the top, group 7A, these are the halogens, another nickname for a column. The guys here in the middle, and again, guys, this is only the top portion of the periodic table, but all the elements here in the middle that I've cut most of them out of, but these are the transition elements, also known as sometimes transition metals, and that's this whole big group here in the middle. And then over here on the far right-hand side, we've got two more columns with nicknames. The very first column, group 1A, is nicknamed the alkali metals. And the second column is the alkaline earth metals. All right, on the periodic table, you'll also notice this big zigzag, thick, I call it stair step, really, but this big line that kind of separates the periodic table. Well, to the left of that stair step, those are the metals. To the right are the non-metals. And then the guys that are in green here, that are actually touching or sitting on the stair step, those are metalloids. There's one little exception, and it's a very common element that sits on the stair step, on the zigzag line, aluminum. Aluminum is an exception. It sits on the stair step, but you'll notice it's not one of these green elements on this periodic table. Aluminum, while it touches the stair step, is an exception. It is not a metalloid, it is a metal. Think about the aluminum foil you've got in your kitchen. I think that'll make sense. Question down here, why is this distinction made between metals and nonmetals? Well, first of all, they have very different properties. One of the many properties, metals are generally found combined with nonmetals in the compounds they form. We're going to look at things like sodium chloride, NaCl. Sodium is the metal, chlorine is the nonmetal. So that's just an example there of what this last sentence says. Here are some examples of the alkali metals. Remember that group 1A, the first column on the periodic table, lithium, sodium, potassium. What I'm showing you here in these petri dishes, they've got water in them. And all three of these metals, they're in the same column on the periodic table. They have very similar properties. They are very reactive with water. And so that's what this is supposed to depict here in the petri dish. Over on the other side of the periodic table, group 7A, where fluorine sits at the top, these are halogens, and three of them, you can see right here, they're in containers, they're a colored gas. So keep in mind, elements that are in the same column, those are the things that go up and down on the periodic table, have very similar properties. All right, here's some characteristics of metals, metalloid, and nonmetals. As I told you, they're different. They have different properties, and here are some of the common properties that they share if you're a metal or a nonmetal or a metalloid. So for instance, my example up here, silver, you can read about the properties of silver, but down here, silver is a metal. That fits in with many of these properties. Metals are shiny and ductile. They're good conductors of heat and electricity. Nonmetals are the opposite, and so guess what? Their properties are opposite. They're dull, they're brittle, they're poor conductors of heat and electricity, but yet they're good insulators. And then metalloids, remember those are my guys that sit on that, oh, that was a terrible line. Let's see if I can make that a little better for you guys. Those are the guys that when you look at the periodic table, sit on that stair step or zigzag line. Metalloids are good, or better, I shouldn't say good, but better conductors than nonmetals, but they're not quite as good as metals. And they sit in between the two on the periodic table, and their properties are in between the two. Sulfur, oops, I had some of my wording fell off here, but sulfur. Sulfur, and we're going to talk about what the numbers on the periodic table mean. Sulfur and all elements on the periodic table have atomic numbers and they have mass numbers. The atomic number is specific for an element. It's kind of like your student number or a social security number. It's the same for all atoms of an element, and it's equal to the number of protons in an atom. So remember those three subatomic particles I said we're going to talk about? Well, here's our first venture into how do we calculate them for any given element. So the number of protons an element has is always equal to its atomic number. Then there's mass number. Okay, that's also on the periodic table. Mass represents the number of particles in the nucleus. Well, can you think back? What sits inside the nucleus? Protons and neutrons. All right, so let me clarify what my sulfur here is supposed to go look like. So sulfur can have a mass of 32 and a number of 16. So if sulfur's atomic number is 16, that means sulfur has 16 protons. All right, well, what about the other subatomic particles? Well, I don't have it on here. However, I have it down in this table. It also happens to have 16 negative electrons. So atomic number is not only equal to the number of protons, but in a neutral atom, it's also equal to the number of negative electrons. 16 positives and 16 negatives, do the math on that, it adds up to 0. All right, that leaves one subatomic particle left, and that's neutrons. And we're going to be able to determine the number of neutrons from the mass. So sulfur has a mass of 32, and the atomic mass comes from protons plus neutrons. So mass equals number of protons plus the number of neutrons. And so we figured out based on the atomic number that there's 16 protons. So the question is, if you can read this through my scribble, 16 plus what equals 32? Well, it just so happens in this example that there's 16 neutrons in sulfur with a mass of 32. Okay? So protons, electrons is equal to the atomic number. Protons plus neutrons equals to the mass. And using those two pieces of information from any element, you can figure out the 3 subatomic particles. Down here is my table, my example here. I've got the different elements, their atomic numbers, their mass numbers, and from there, that hopefully you can see where each of the 3 subatomic particles was calculated. All right, again, please forgive my formatting here, it's a little off. We're going to talk now, or briefly here, about isotopes. And let's skip the chlorine, or the carbon, that's supposed to be carbon actually for now, and let's just look at lithium. We'll keep it simple. So isotopes, same element, different atomic mass. So for instance, for lithium, there's 2 isotopes. There's lithium with a mass of 7, and there's lithium with a mass of 6. So lithium's atomic number, and any isotope's atomic number, is always the same. Remember that number never changes, like your social security number. Always the same, your student number, always the same. So for these 2 different isotopes, we're going to have slightly different numbers in my subatomic particles. Now, not completely different, as I said, slightly different. So protons are always the same. Protons equal to the atomic number. And it's equal to the number of electrons. I'll abbreviate since I'm running out of room up there. And you go, okay, so what's the difference? Well, that leaves me with 1 subatomic particle left, my neutrons. And remember, atomic mass, or mass number, is equal to protons plus neutrons. They're not equal to each other. Sometimes they are, but not usually. So if my mass, for instance, in this guy is 7, 7 equals my 3 protons plus what? So 3 plus 4 equals 7 for this isotope of lithium. For the other isotope, where the mass is 6, right here, I still have 3 protons. 3 plus what is 6? Well, 3. So in this particular isotope of lithium, there's 3, 3, and 3. Versus lithium, when it has a mass of 7, has 3 protons, 3 electrons, and 4 neutrons. How does that sound? Does that make sense? All right, if it does, then this should be pretty simple. Now let's look at the mess here I have for carbon. So carbon 12, carbon 13, carbon 14. And I'm going to do a table here. We're going to do number of protons, number of electrons, and number of neutrons. And what I really want you to do, I want you to see if you can figure this out. I want you to pause the slide, and then you can come back when you're ready to check your answers. All right, if you're back, so carbon has atomic number of 6. So regardless of what isotope of carbon we have, there's 6 protons, 6 electrons. Where does the variation come from? Again, it comes from the neutrons. So if I have a mass of 6, protons plus neutrons equals my mass. Mass is 12, protons is 6. In carbon 12, this first guy here, I must have 6 neutrons. In the next one, I have a mass of 13, but yet I still have 6 protons. So 6 plus 7 equals 13. And finally, in the last isotope, I have a mass number of 14. So 6 plus what is 14? That's right, it's 8. So looking at this other example for carbon, carbon actually, as I said, has 3 isotopes. And there's nothing to tell you, explain why lithium only has 2, carbon has 3. It varies depending on the element You would never be asked that. You'd always be given the information about the isotopes. But once you have that, you need the atomic number, which again never changes for a given element, and then you need to know the mass. So you would need to know the mass number for the different isotopes, and from there you can figure out your subatomic particles. All right, so what I was just talking about, the isotopes of different atoms. For instance, magnesium up here. Magnesium comes in 3 forms. Magnesium with a mass of 24, magnesium with a mass of 25, and magnesium with a mass of 26. Now, what's on the periodic table? Well, we call that an atomic mass or a weight. Where does that come from? The number that's on the periodic table, well, that's where we're leading to, or I'm leading to with this discussion. So again, let's just clarify again, what's an isotope? Same element, same atoms, but they have different mass numbers. So same atomic number, same number of protons, it's the number of neutrons that varies, and that's what we just saw. Isotopes, as it says, are very difficult to separate from each other, so they only occur in any sample of the element in their natural abundance, which remains relatively constant regardless of where you got it. So what that means, if you think about the magnesium, what that means is wherever you get the magnesium, whatever it is, if it's magnesium, it's going to have a relatively same percent of the abundance of the 3 different isotopes that are found. And then here's something interesting, and we're going to come back to this in a few chapters. Most but not all isotopes are stable. If it's an unstable isotope, we refer to it as being radioactive. You guys have heard that term, right? When we come back and look at our nuclear section and talk about nuclear medicine, for instance, we're going to come back to this. Okay, so let's look at what's going on with chlorine just as an example, and the numbers on the periodic table. So on the periodic table for chlorine, this is what the box with the information looks like. The question is, how did they get the mass of 35.45? Okay, well, as it says, since a handful of chlorine, there is a mixture of 2 isotopes. This isotope with a mass of 37 for chlorine, and this isotope with a mass of 35. You can see the abundance is shown in that, what I just circled, and an average atomic mass has been defined. So what in the world does that mean? What's on the periodic table? That's the average atomic mass. It's based on the individual isotopes, their masses, and the percent abundance. So for instance, this is chlorine 35. Hopefully you can kind of see that there. Chlorine 35 is found about 76% of the time. So about 76% of all chlorine atoms on the planet have a mass of 35. That's where this info comes into play. I took the 75.76, divided it by 100, got it into a decimal number, and then I'm going to multiply that by the isotope that goes along with, which is 35. Chlorine with a mass of 35 is found 75.76% of the time, but I need to get rid of the percentage. So 0.7576 times 35, that's for the first isotope. And then the second isotope, which is chlorine 37, and for chlorine there's only 2, so it's found 24.24% of the time. The percent abundance for that, as we would say, 24.24. So 0.2434, this looks like a little bit of a typo, go with it though, times the mass of 37, which is the mass of this isotope. This is the second factor. Add these 2 together, and that leads us to our average, which is 35.45. That's where it comes from. Little kind of side notes here. Since most elements on the periodic table have stable isotopes, means not radioactive, most atomic masses are not whole numbers, but rather they're averages of the atomic masses of their isotopes adjusted based on their natural abundance. That's what we just did here. There is one exception, you don't have to really know this, but just FYI, is fluorine. Fluorine 19. Fluorine only has the 1 isotope. Here's just, again, kind of FYI information. Some common elements lithium, carbon, oxygen, fluorine, sulfur, copper, and they're natural occurring isotopes. And as I said, some have 2, some have 3, some even have 4, and we have just one that only has 1, and that's fluorine. You can see what their averages are based on the mass and the abundance, which the abundance isn't listed here on this table. You'd have to have that to be able to do the calculation. Now, what you can do, however, and this question right here says, which of the isotopes listed above for each element do you think is the most abundant? So let's go back for a minute. Think about the chlorine 35 and 37. The average for chlorine was 35, about 0.5. And do you remember which of the two, chlorine 35 or chlorine 37, had the larger percent abundance? That's right, it was chlorine 35, had an average abundance of about, I don't know, what was it, about 76%. And notice that closely resembled what the average was, what was reported on the periodic table. So in other words, here's what we're going to do. If this is what's on the periodic table for lithium, 6.941, and there's 2 isotopes of lithium, lithium 6 and lithium 7. Since this is so close to 7, I'm going to guess with good certainty that the largest, most common, however you want to say it, for lithium, the isotope of lithium, the most common is lithium 7, because it's closest to the average, the weighted average. Does that make sense? Okay, let's think about it then for carbon. Carbon on the periodic table is reported at 12.01. Ooh, that's right on the money. Which one does that match closest to? Well, that guy, carbon 12. And yes, carbon 12 by far is the most common isotope of carbon. All right, let me erase that for you. Can you do oxygen? Periodic table reports its atomic mass is right at 16. So which of the 3 do you think is the most common? All right, I think you get where I'm going with all this. All right, the model of the atom. What does an atom actually look like? I talked about this at the beginning, and we're going to come back to it now. So you've got this little tiny, tiny, tiny nucleus. That's the little guy sitting here. And all around it are the electrons. The vast majority of the space an atom occupies comes from where the area where the electrons are. Electrons, as it says, are negatively charged. They're believed to be distributed around the nucleus, since it is possible to remove an electron by various means, that would be chemical reactions, and form new species which are positively charged. Furthermore, there's experiments that suggest most of the mass of an atom is located in that tiny, tiny thing we know of as the nucleus, and the vast majority of the space is actually relatively empty. Again, think about that analogy with the football field. All right. Wow, I'm going to jump from that to light. Well, you'll understand in just a second here. So light, what is it? Well, we know quite a bit about it, don't we? Everything we know about our universe comes from the study of how light interacts with matter. We know light is referred to as electromagnetic radiation. This is the electromagnetic spectrum here. Light has both wave properties, and particle properties. All light, whether it's a radio wave or visible wave, light travels at the same speed, 3 × 10⁸ meters per second. As a result, since the length of each wave decreases from left to right, the frequency of the peaks and troughs, that's these guys here, okay, and then this guy here, must increase from left to right. We referring to light as a particle, known as a photon of light. The energy of each particle of light is also known to increase from left to right. So this is big here, guys. Again, energy, energy, energy. The total energy, though, of course, depends on the frequency of the light and the number of particles. We're not going to get too involved in this, but let me just clean this up for us. Okay, so all of this involves energy. Now, let's just use some common sense here. Is it dangerous to be exposed to a radio? Literally as in like radio waves, like listening to the AM, FM radio? No, it's not dangerous. There's very low energy associated with those waves. Now let's go to the other end. Let's talk about gamma rays, X-rays, cosmic rays. Can that be dangerous if we're exposed to too much of it? You betcha. It's very, very high in energy. In fact, it can damage our cells, it can damage our DNA, it can do a lot of damage. So that's what we're kind of talking about here. How does this tie into the atoms, electrons? Well, we're getting there. So light also has a magnetic field associated with it. You know about magnets, so that's what we're talking about here. It varies in the same fashion as the electric field, traveling at the same speed but perpendicular to the electric field. Both the electric and magnetic fields are used in medicine. Most of you want to be in medicine? Well, this is your first introduction into this. How about MRI? Have you heard of that before? Well, MRI stands for magnetic resonance imaging. And the picture here is an MRI of a heart and lungs using radio wave frequencies in the presence of, and here's the key kicker here for the MRI, obviously not just being exposed to radios is going to do this, but in the presence of a strong external magnetic field. So they use magnets to line up the electrons in our bodies. White light that passes through a prism is separated into all the pretty colors. You guys can all see this here. Called a continuous spectrum, and it gives the colors of the rainbow. When an element is heated, it actually gives off light. Did you know that? However, the rainbow of colors is absent and only certain colors are present. Well, each element has its own properties. This is one of those things. Each element also gives off its own spectrum of color. Not all of the light is in the visible region even. Remember back to that previous slide, the visible region was only a sliver, just a small sliver in the electromagnetic spectrum. Depending on the temperature, the element, some light covering a large portion of the electromagnetic spectrum can actually be observed. Now, what I'm showing you here, let me kind of try and blow this up a little bit. This is strontium. So we heat up strontium, like put it in a flame, and it actually emits a light, and we see it as a pretty red light. That's strontium. Barium, another metal sitting over on the left-hand side of the periodic table, different metal, has different properties, and it gives off a different colored flame. You can see this is the spectrum here, okay? But what you would visibly see to your eye for barium, you'd see a green flame, and strontium, you'd see a red. Does this give you ideas maybe about fireworks and the colors and things that they do with the different fireworks? Well, they've actually devised a model to explain this. It says, think of the model as a bookcase with each succeeding shelf getting closer and closer. Here's my bookcase that I'm talking about. And the succeeding shelves mean, notice shelf 4 and 5 are closer to each other than, for instance, 1 and 2 are. Depending on the element, different electronic transitions can be observed. The emphasis here is electronic. The electrons are being excited to different levels. So let me skip this here a second. Let's go back to the bookcase here. Imagine I have an electron in, let's say it was that strontium atom, and I stick strontium in a flame. What am I doing? I'm applying heat. In fact, a whole lot of heat energy if I stick it in a flame. The electrons grab a hold of that energy and they jump up. It's kind of like hot potato. The electrons that maybe were down here on this first level of the bookcase grab the energy and jump up. And eventually, they're going to let go of the energy. When they're up here, we call this being in the excited state. Down here, in their usual level, whichever their level is, we call it ground state. But when it jumps up, because it's holding that extra energy, we call it excited. Well, as it releases, it holds on to that energy as long as it can. As it releases the energy falling back down to the ground state, it releases what's known as a photon. And that photon is what's tied to and where we get our visible light, where we see the different colors. All right, let's go back to the periodic table then. Everybody's seen it, you've looked at it. Let me tell you a little bit about it. The periodic table is named periodic because it has been known for a long time that many of the chemical properties of the elements are very similar, but then also very different from each other. And that's why they're organized the way they're organized. In fact, they're organized in all sorts of different ways. We've already talked about the columns, technically called a group. For instance, noble gases. These guys here on the end, they have very, very similar properties. And even though they sit over here and, well, yeah, neon is a nonmetal and fluorine is a nonmetal, these two, neon and fluorine, are actually very different from one another in terms of their properties. So the theory has been developed to explain this periodicity, we call it. It's mathematical in origin, so we're going to simply look at it as a model. All right, on closer inspection of the different levels on my bookcase, I'm jumping back to this here, additional fine structure is observed within each N level, okay, the bookcase, and they're assigned different letters of the alphabet. All right, hang on a minute, why am I even talking about this? Guys, this is all related to and tied to the electrons. The electrons that sit outside the nucleus in this vast, essentially empty space. In fact, they're moving around outside the nucleus, and they're in these things we're leading to called orbits. Okay, and that's what we're working on this. All right, so we have figured out the following, and that is that there are let's say orbits, there's S, there's P, and there's D, there's even F. Technically they're called subshells, but they have different shapes associated with them. And these are, I kind of like to call it, if you think about a bookcase or maybe think about this like an apartment building, the S, the P, the D, and the F, these are all different, let's say, shapes, sizes of apartments, okay? The S is a 1-bedroom apartment. The P is a 3-bedroom apartment. The D is a 5-bedroom apartment. And the F, even though we're really not going to get into the Fs, but guess what? 1, 3, 5, can you do your next number? That's right, a 7-bedroom apartment. Okay? So I have different floors on my apartment building, and I have different apartments. Now, what are the technical terms for this? The levels on my apartment building, first floor, second floor, third floor, these are called principal energy levels. The different types of apartments, the S, the P, the D, and the F, these are called sublevels. And then if you notice, I've kind of done these little boxes here, and that's going to be important in a second. The different boxes indicate the different bedrooms. Remember, S is 1-bedroom, 1-bedroom, 1-bedroom. P is a 3-bedroom, so notice I have 3 green boxes next to each other. D was a 5-bedroom, 1, 2, 3, 4, 5-bedroom. That's going to be important in just a second here. Now, one other thing, and let me erase this here, some of my scribble. Okay, think about a bedroom, a standard bedroom in an apartment building. 1 bedroom. What do you think the maximum number of occupants that we would allow to live in a 1-bedroom is? 2 occupants. Okay. And dumb analogy, I like to do lots of dumb analogies. My 2 occupants, the occupants are my electrons. Okay? We're trying to figure out how these electrons are ordered, where they go outside the nucleus. That's what we're getting with all of this. So as I said, the S, the P, the D, the F, they're all different. They're different in shape, too. This is an S. An S is a sphere. It's a sphere. The P, well, P goes on the 3 axes, the X, the Y, and the Z. And in fact, so they're separated here just to show you, but really the X, Y, and Z axes in 3-dimensional space overlap. Now, what these things look like? They look like balloons. What in the world are these orbitals or orbits? Well, as it says right here, here's what they are. The theory is it's just simply a region of space. One is likely to encounter an electron. So it's the highest probability. So in other words, if we think about this 3S sphere, I've got electrons moving around, all around, crazy, crazy, crazy. And they're just at least the ones that are in this particular orbit, they're likely to be somewhere in the spherical shape around the nucleus. If I come over here to the P, I've got electrons also, but they are in a little bit different shape in terms of, again, probability that the electron is somewhere around the nucleus like that. Okay, so we're leading to electron configuration. I've gotten my slides a little screwed up, so I apologize if I become redundant here. We're leading to writing out electron configurations. And what is an electron configuration? Well, it's where the electrons sit, where they're located outside the nucleus. We're not really going to ever go beyond atomic number 20, which, remember, atomic number is equal to the number of protons and equal to the number of electrons. But we've got to figure out what the electron configuration is for at least the first 20 elements on the periodic table. Now, my little diagram down here, it's kind of a sad way to show this, but I'm going to use this to show you how we fill in and figure out these electron configurations. Now, you got a couple of rules you have to keep in mind. Remember, S apartment, 1 bedroom, it's maxed out at 2 electrons. P's are 3 bedrooms, 3 times 2 occupants, maxed out, at 6. And if I need to, my D's, D is 5 bedroom, 5 times 2, it's maxed out at 10 electrons. Now, you fill from the ground up, from the bottom up. Remember your bookcase, n equals 1, closest to the ground. You fill that first. So you fill the 1s first, then you fill the 2s, then you fill the 2p here, then you fill the 3s. Okay. So notice I'm first floor, then I'm on the second floor, then I'm on the third. And you go, but wait a minute, what about, how do we know S's, P's, and D's? Well, the first floor, the first principal energy level, 1, first floor only has 1 type of an apartment, an S. Second floor has 2 types of apartments, S and P. Third floor has, you guessed it, 3 types of apartments, and so on and so forth. We're not going to get anywhere near that involved. We're going to keep it real simple, you guys, and we're only going to place at most 20. So you basically just need to remember, let me get rid of some of my squiggle here. You basically just need to remember, my eraser's not working. The basics and fill in the electrons where they're needed. Okay, so if this is my basic, okay, and you're going to start here and fill then from left to right, but remember the rules. S's are maxed at 2, P's are maxed at 6. So let's just pick and choose. Sorry, I got my little numbers scribbled over here. For instance, helium. Helium is atomic number 2. It has 2 electrons. So we would say the electron configuration for helium is 1s. What can S's have? 2. And in fact, that's it. Helium just has 2. There's 2. We're good. That's the configuration for helium. What about for, let's jump to carbon. Carbon is 1s2. That's filled. 2s2, that's filled, but 2 plus 2, I only have 4 electrons I needed to place, if you can read that, 6. So now I open up the P apartment and I put 2 in there. 2 plus 2 plus 2 is 6. Carbon is atomic number 6, has 6 electrons I needed to place. There's the configuration for carbon. Now let's do it for sodium. Let's get real crazy. Sodium is atomic number 11, so I need to write a configuration that shows where 11 electrons are. And remember, you fill in this particular order, and you can never open the next one until the one below it is filled. So again, come back here if you need to. 1s fills, then the 2s, then the 2p, then the 3s, and then if you need to, the 3p. Okay? So hopefully you see how electron configurations go. And guys, you're online for this part. If you're unsure, you need to know electron configuration for sodium, Google search it. All right, so this kind of expands what I was just showing you, the boxes. We're going to not get to the F's at all, I'll tell you in here. The D's, just maybe a little tiny bit, okay? Here's though something that is important. It's going to be really important for when we go on to the next part of the class, and that is we need to be able to identify what the valence electrons are in any given element. Even if it has more than 20 electrons, there's a really easy way to figure out valence electrons, but well, let me back up first. What is a valence electron, and why do we need to know what they are? A valence shell, also called valence shell electron, they're the outermost, highest energy level electrons. Okay, so if you think about electrons in the here's my nucleus. If you think about them, a lot of people do, unfortunately, but we'll go with this thinking. If you think about them like rings around Saturn, okay, the valence would be the highest, the outermost electrons. Those are the ones I'm interested in because they are the ones that determine chemical properties, which means reactions. It's the outermost electrons that mix with other outermost electrons. Give or take, they're exchanged, they're stuff we'll get into later, but that's why they're so critical. So how do we figure out valence shell? Well, if it's written out like this pretty one here, you find the highest level and you say, how many valence does this, whatever this is, have? It has 1. 1 electron on the 3rd floor. That's its valence electron. That's all it's got. It's got the 1. On a periodic table, there's a really easy way to figure it out, and that's based on the location on the periodic table. We'll talk about it on the next slide. Okay, so a couple of things here. Let me finish up the valence electron, for instance, or slide. So I've got to add some numbers here to the top, and even though these numbers are not on this particular layout, and I'll explain what this one's about, I wanted to show you a shortcut for valence electrons. And that is find the group number. That's at the top of the column on the periodic table. That's how many valence electrons any particular element in that column has. So for instance, where's carbon? Carbon sits right here. Carbon has 4 valence electrons, and everything in the carbon's column has 4. Fluorine sits right here. Fluorine, chlorine, bromine, iodine, the halogens, guess what? They all have 7 valence electrons. Okay, so that's your shortcut for figuring out valence electrons. Remember that. I'll bring it back up when we need it again when we do Lewis structures, but for now at least just keep that in mind. Okay, let me erase this then and just show you a summary of the way the periodic table is laid out. As I said earlier, periodicity, the periodic table, the elements are laid out for a particular reason. One of the cool ways about the periodic table, why do I have like a set of columns here, this chunky thing in the middle, these guys out here, the guys over here? Well, it's based on electrons. Electrons. And for instance, remember the S's, my S apartments? How many occupants could an S hold, an S apartment? 2. How many could a P apartment? P had 3 bedrooms, each bedroom maxed out at 2. 3 times 2 max is 6. D's were a 5-bedroom apartment. 5 times 2 is 10. And F's, if you remember, even though we're not going to do much with them, but I'm going to show you this in a second, F's have 7 bedrooms. 7 times 2 is 14. Now take a look at this. How many columns are in the S block? 2. How many columns are in the P block? 6. How many columns, if we add them all, are in the D block? 10. And how many, they're short little stubby things, kind of like me, how many columns are down here in the F block? Well, if you added them all up, there's actually 14. Where in the world, how does this play into what I'm talking about? Well, electron configuration. So for instance, fluorine, let's just pick on fluorine. Fluorine sits right there on the periodic table. Fluorine is atomic number, I got to think about what it is. I think it's 9. Fluorine is number 9. So if we were to write out fluorine's electron configuration, it would be 1s2, 2s2, 2p, can you figure it out? 2 plus 2 is 4. I need 9, so 5. This is fluorine's electron configuration. Well, if we were to look at the periodic table and where fluorine sits, it sits in the P block, sits over here in this green section called the P block, and it sits 1, 2, 3, 4, 5 columns over, P block, 5th column, and it's on the second floor. So imagine that bookcase, I just flipped it upside down. Here is floor 1, here is floor 2, floor 3, floor 4. You can see where I'm going. So fluorine sits on the 2nd floor, sits in the P block, and over in the fifth column of the P block. Well, guess what? That matches its electron configuration. And that works for any element on the periodic table. So some people, when they do electron configuration, they actually use that. They figure out where it sits, so 2nd floor, P block, 5th column over, and they say, okay, its last is 2p5, and if that has electrons in it, everything else before it must be filled. And what comes before the 2p? We'll work your way backwards, the 2s. What comes before 2s? Well, the 1s. And again, you can do that for any element. And so there's a couple of different ways for you to figure out electron configurations that I've talked about. I hope you have enjoyed this talk.